Hey guys, and welcome back to a new video. And this is a video I am particularly excited about because it's just so interesting on the one hand, but it's also a topic that is really important for any Android developer who at least wants to seriously publish an app at some point or works on behalf of a company that wants to seriously publish an app. Because today we will really have a deep dive into security on Android, specifically into reverse engineering. And I can already say, if you have an Android app in release build and you enabled obfuscation for it, so here in your Gradle file, you turned on isMinify enabled to true, which pretty much just renames all those classes, function, variable names in your code to very short, unreadable names. If you did that and you think that this protects you from reverse engineering because it makes attackers browse through your code much harder, since that is what reverse engineering is. An attacker would try to extract back the original source code of a final APK in order to extract secrets of your code, like API keys, cryptographic keys, in order to maybe change its behavior. If you think that using R8 and ProGuard here makes your code safe, then I can already say you are wrong. And in this video, you will get a really detailed explanation with a practical deep dive into reverse engineering on why that is the case. And at the end, I will then, of course, also tell you what you can actually do to make it virtually impossible for a reverse engineer to actually extract your secrets and really do serious harm to your app when they get access to your APK, which, by the way, anyone could get if it's published in Google Play. Specifically, I will show you 3 different approaches to what an attacker could do in order to crack your app, in order to extract sensitive information from it. So you get to learn those 3 different perspectives of what could actually go wrong. For this video, I will make use of a little sample APK that we will kind of hack together here. If you want to follow along, which you absolutely can, all the steps here will be outlined. Then I will also link a GitHub repository with resources specifically with this APK, but there's also a file we will get to later in this video what this will do. But specifically this APK, which is in the end a release build of an APK that has already turned on obfuscation. So that has turned on this isMinify enabled, because I really want to show you that this does not make your app safe. So let's take this app, install it on an emulator. It's a bit of an older APK build. So make sure that you're not using an emulator with the latest API level, then it will crash. I'm running on API level 30, that is working perfectly fine. So just to show you what this app actually is, here we have this uncrackable APK, and in the end it's really just an edit text field here with a button where we can enter a secret string, where if we enter something like hello world, click verify, then it says, okay, that's not it, try again. So there must be some sort of specific secret string that we need to enter here so that the app lets us pass to some kind of other screen, for example. And in the real world, that might not be a text that you enter in an edit text to get somewhere, could be, but it could also be an API key that you enter in your app. So if your app interacts with some kind of remote backend, you have an API key baked into your app source code, and your company may be paying for that API key. If an attacker now actually gets access to that API key, what that would mean is, that would on the one hand mean they could just make requests to that API by you paying for it or your company paying for it. And even worse, they can make requests in your name, because an API key typically also includes some sort of authentication information who is making that request, so that it's your company that is making that request. And depending on what kind of API that is, the attacker could of course cause a disaster for the business if they kind of abuse that API key and make requests they shouldn't make. For example, if they could use that API key to send emails to your customers, that would be a disaster. So I think it's clear why it's so important to actually protect your app against reverse engineering. So let's see how that actually works. A lot of time we will spend in our terminal today, because we will make use of various different tools that can help us to actually extract this type of secret here in the app. So what we would need to enter in this edit text to pass this dialog. And with the first of the 3 approaches of reverse engineering that I want to show you here, we will really just try to read the original's APK's source code and try to understand what happens there in order to get to our secret. So how could this work? How can we actually get that kind of source code, or at least a variant that is close to the original source code of this particular APK? As I said, you can download it on this GitHub link below. We want to do this with a tool called JetX. So you can actually download a JetX here on Google. It's a source source, but I think there are also different websites to download this. I will include a link to this down below, but it's in the end a so-called Dex to Java decompiler. So the Dex files on Android are the so-called Dalvik executables. So when we type our code in Java or Kotlin, then these instructions are actually translated to a bytecode, specifically to Dalvik bytecode, as you can see here. which is the bytecode variant the Android runtime then understands and will execute. But this is in the end a tool that provides us a visible user interface to browse through the original file contents of an APK, or at least something very similar to the original file contents. So let's use this tool. So I've downloaded this, installed it. By the way, I'm using macOS here. I'm pretty sure on Linux it will be very similar to what I'm doing here. On macOS, the terminal is also Unix-based. For Windows, I'm not entirely sure. You might be able to do the same with the git bash, which is a bash that is very close to Unix-like terminals. But be aware that I'm doing this here on macOS. So I've downloaded this JADEX tool here, and then ran it and installed it, which is here in this folder. So I've just extracted that. We can go to the binaries and then double-click here on JADEX GUI, so the graphical user interface. Then it will open another terminal window. We can move that away. We don't need this, but keep it open because now an actual window will open up here, which is the JADEX program. And now here in this window, we can open our terminal again, navigate back to our crackme folder or whatever folder you have this APK in, and simply take this APK and drag it into this window. Then you can see we effectively extracted this APK in some sense. And here we have a package called source code. That's interesting. Let's take a look at that. So source code, there we go. There are two packages here. This looks like an Android package name. Let's open that. Okay, uncrackable also looks like something of the app. Okay, main activity. That's interesting. That's something we've heard before. And another apparent class that's called A. But here you can see this is source code we effectively extracted from the APK that I gave you. So this is the code that was extracted here from this APK with this dialog and this edit text check that I showed you before. And the interesting thing we can now already see here in the source code is that name obfuscation has been applied. So that's exactly what is achieved by turning on isMinify enabled, so setting that to true here. And don't be confused, this Android Studio project is not the app that is launched here, but we will do something else here. But turning on isMinify enabled will result in name obfuscation. So, for example, here, this is a function call that was definitely not named A in the original code. But what the tool R8 actually did, that is what actually obfuscates this code, it takes all those function names, variable names, class names, and renames these to very short, unreadable names, like A, for example. Or here, take a look down here, we have A.A. Or if we open this other class here, then we have a class A with a function A. We have another function B. So this, of course, achieves in some sense that it's a bit harder to navigate this code. But what most people don't know is that R8 is not meant for security. This name obfuscation, the main purpose of that is really just that the final APK size will shrink. It's a code optimization tool, but not a security tool. Because obviously, if your source code has a smaller length by having shorter variable names and function names, then it will occupy less size. And even though we applied R8 here, you can see it's quite readable code. So let's try to understand what happens here. Going back to main activity, thing is we can already see actual strings as they are in the app. For example, down here, that looks very suspicious, where we see, okay, this is the correct secret. So this already gives us a hint where we actually need to look in the code in order to bypass this, or in order to maybe print the secret or get this as an information. So here we have an if check that checks if A.A with the object being passed, which seems to be the edit text string here, so what we entered in the text field. So we pass the string to some kind of function call called A, and if that returns true, then the dialog will say this is the correct secret. So let's take a look here in this A. So just double click on that, and then it will open here in this other file. That's the function we've seen before. And here a lot of stuff is happening. So we see two strings, but that doesn't seem to be the secret in plain text. So there's some base64 decode. It also calls this function B here down below, which does some byte transformations, some bit shifting. So it's certainly not something that we would understand right away. But in the end, what we see here, that's just Java code. So what about we take this code, copy it, and just have another Android Studio project, which is the one I've prepared here, which is a Java project because the decompiled code is Java code. So make sure to not create a new Jetpack Compose project here, because then it's by default a Kotlin one, but make sure to just have an empty activity with a Java code, and then we simply paste these two functions here. So of course we can remove the package name here. We have a different one, remove this. This A, let's take a look at what that was in the original code. So this A, we can take a look at that. Okay, that's apparently another type of class that we haven't yet considered. And you can see this contains some cryptography, some encryption. So let's also take this function, copy it, and actually include it here in our Android Studio project. Down here, we can rename this to something like crypto or so. We don't yet know what it does in detail, And we get some warnings, but that's really just because these function calls could throw exceptions. We can just hit Alt-Enter, add exceptions to function signature. Same for cipher.init. This is really not to build a well-structured project, but to find out that secret, of course. And this crypto function was the one that was called here, right there. So here we had this other class A, and from this other class A, the function A was called. So we say crypto of this here that we passed there, and suddenly we don't have any syntax errors anymore. So if we now take a look at this function A, which checks whether we entered the right secret, the return value is just a string equals check. So it compares the byte array here, this one, with the string that we passed. And this string that we passed here is what we entered in our edit text field. So what we actually need to know here is this byte array and its contents. So what if we actually get rid of this function and just execute this function's code here directly in our own create call? We put this in here, and instead of having this return call, we simply want to print the contents of this byte array. That is the result here of all this cryptographic transformation. So we could say system.out println, so we just want to have a console println statement, and we say the secret is, and we say plus a string, and we simply take our byte array, actually make that a new string, I'm used to Kotlin, but add a new string, we take our byte array, convert that to a string, and then we print this. Let's try this out. We run this in our project. There we go. The app is launching. It's really just a sample Hello World app, but with our code, it does not crash. That's pretty good. Take a look at Logcat, and here we see the secret is I want to believe. Let's take a look. Let's copy that, open our original app, and try if that's actually correct. So uncrackable again, that's the original app. We go in here, we clear the text field's content, and type I want to believe. Click verify, and that's the correct secret. So you can see, even though we had all that name obfuscation, and we had all that bit shifting here, complex byte array with encryption, that was still fairly simple to get access to that secret. So this is one approach how an attacker can reverse engineer your app. They can simply use JetX or so, a similar program that tries to extract back the source code of your app, and they can then freely browse through it. And even though you might have applied R8, you just saw it's still very readable. And then they can just copy or extract certain parts, experiment with that in their own project, and then get to the secret that way. But that's not the only way how an attacker could approach this. There are two more ways that I want to show you. The next way that I want to show you doesn't actually require reverse engineering on our own at all, but rather what we want to try is we want to try hooking a function. What does hooking mean? Well, we will actually take a look at the application in runtime, and during runtime we want to achieve that we can swap out the implementation of a specific function with an implementation that we define. So what we can achieve with that is, for example, that we can hook the string equals function, so whenever two strings are compared, and say, okay, you still compare those two strings, but in addition, simply print those strings, so that when here our string equals function is actually executed, this equals call actually also prints this string and the byte array, those two strings that are compared. And this we can achieve with a tool called Frida. So first of all, opening the terminal, what I want to do is I want to navigate to the actual folder where I have this actual original APK. So it's in downloads, crack me for me. There we go. Here's our uncrackable and this hook string equals that will become relevant now. And here you first of all need to make sure that you have this Frida tool installed. It's called Frida. You can install this simply with a pip install frida-tools. Another tool you will need in order to follow along with this is the so-called objection tool. So also type pip install objection, then install that on your machine, and then you can follow along. And this is, by the way, also what we need to start with, because Frida can't just run aside with the original APK, but it actually needs to kind of inject certain source code into that APK that allows us to modify our code at runtime. And this is what we achieve with objection. So it generates a special kind of APK that we can then run and have this Frida tool, Frida gadget being used for that. In order to use objection, you need the AAPT tool, which is the Android packaging tool, available here on your class path. So if you have Android Studio installed, you also have this tool installed. If you type which AAPT and it says something like AAPT not found, that does not mean that it's not installed, but it's really not just on your class path. So the path for executables where the terminal tries to look for when typing a command. In that case, you would need to export this first. So you simply paste this, export Android SDK root, and you can really just copy paste this as it is. Here under build tools, this AAPT tool is likely to be located. But if we just hit enter here and then type source, with this .zshrc. That way we can just reload those environment variables, or these, not environment variables, but with this tool we can really just reload this path variable so we know it in this terminal, and then we will be able to use AAPT, so which AAPT will now print a proper path here linking to this tool, so we could directly use this, which will now be used under the hood by this objection tool. So now we want to say objection patch APK -- source, and here we now enter the actual path to our APK that we want to generate this objection APK for, which is in the end just our uncrackable level 1 original APK. We hit enter, and then objection will do something. Takes a little moment. Here we go, rebuilding the APK with this Frida gadget loaded. And there we go. If everything worked, this is how it should look like for you. Let's clean this up a little bit. And if we now type ls, we will also see that we have another APK version here, which is called objection. And this is now the APK that we need to install on our emulator here instead of the original one. So if we open our Finder again, we take this objection APK now, drag it into the emulator, then we do get this kind of issue here because it says, okay, the objection APK actually has the same package name as the old app, but it's signed with a different key store. So what we effectively need to do in order to fix this is uninstall the old app so that there's only, that the objection APK would kind of be a new APK for this device. So just uninstall this, drag in this objection APK, and now it was properly installed. So now if we open this new uncrackable APK here, you will notice that it won't do anything for now because it will wait for the Frida gadget to actually hook into this process of the app, and that's what we now want to do. So again, hopping into our terminal, what we now want to do is we want to actually take this hook string equals, which is a JavaScript file. That's how the Frida tool actually expects this to be in. We can check its content here to just see what this does. So it's really just a function call in JavaScript to take the string class here, Java language string, and actually replace the implementation of the equals call for two strings with a function implementation that we define here. And in the end, this function implementation will really just still execute the equals check and behave normally to the outside. But in addition, it will print all of these parameters, like the strings that are compared, print that on the console. And with this hook function, we now want to actually find out our secret. And that works as follows. We use our Frida tool, we say -u. That means we want to connect to a USB device. Make sure that only one device is running here. So if you have this emulator running, make sure there is no other connection from your physical device or two emulators running. Just make sure you have one. Then we say -l to define this hook file, which is the hook string equals.js. And the last parameter that this Frida tool expects is the actual name of the process of our application that we want to inject this hook into. And the name of the process is really just the app name itself. So you can see on the left, it's uncrackable1. So we just define uncrackable1 here, hit enter, and then waiting a moment, and suddenly we can already see that there are lots of things being printed. So string equals was called a lot of times here. You can see sometimes with insert source. So deep down in the Android SDK, that was obviously called quite a few times here. It wasn't yet called for our actual real check for this string, because that is only made once we hit verify. So let's just enter anything here, hit verify. Well, that's not it, but if we take a look in the terminal, we just now really need to look for what could look like a secret. So going up here a little bit, and here it is. We see string equals called. This is test. We could, of course, also filter this for the string we entered to make this a bit faster. But the other one is I want to believe. So test was compared with I want to believe, and there's our secret again. In this case, we didn't even change the source code in our own in any way. The Frida tool somehow did something that it could inject this code, but we didn't need to understand the app source code at all. So what is the real-world connection, the real-world learning of this? That means you can apply as much static protection in your code as you want. You can encrypt your code, you can encrypt certain secrets, but anything in your code can be overwritten by an attacker during runtime. And it doesn't help you a bit if you have encrypted secrets in your source code and you can't read these as plain text when decompiling that. If you can just print the decrypted string during runtime with Frida, so you can really change a software's code during runtime the way you want. If you have a video game, that means you can move through walls by just changing the code that checks, is that a wall? You can change the amount of money you have in a video game. You could remove ads from an app by just hooking the function that shows these ads to maybe not do anything. So that's option 2, how we can reverse engineer an app and get to such a secret. I still want to show you a third option, and that is that we can change and repackage the APK's behavior on our own. Here with Frida, we injected certain extra checks or extra function calls in the app during runtime. But what if we actually have source code like here that we've seen in JetX and want to change this and repackage that into a final APK that works again? Let's see how that works. So you can simply type quit here and then Frida will finish. We can clean this up. So for the last way of reverse engineering that I want to show you here before I of course also show you how you can protect your app to make it virtually impossible for someone to do it as easily as we did. The last way here, we need another tool that is called APK tool. So while the JetX GUI is useful to actually inspect the source code of an APK, it isn't able to actually repackage that into an APK again and run that on a device. For that, we need APK tool. If you don't have APK tool installed on macOS, you can just install it with brew. So brew install APK tool. Or if you're in Linux, just type it in Google APK tool download, and then you will find a script for that. And what we now want to do is use this APK tool. Say we want to decompile an app, specifically an APK that we now link. And the APK that we link is our uncrackable APK. Actually the original one, not the objection one. So we want to take the original obfuscated app, hit enter, then it will do something. If you now type ls, then we can actually see a new folder being created here. Let's take a look in the Finder. That's a bit more understandable. So we have this uncrackable level 1 original folder. And here we now see all those extracted contents of this APK. It's similar to what we saw in JetX, but it's different. Here we have those so-called Smali files. So Smali code is in the end a human readable representation of bytecode, so the actual underlying instructions of our source code. And this Smali code we can now directly modify. It has its own kind of syntax, so if you really want to do this professionally or so, then you need to learn Smali. But for the sake of this tutorial, it will be a simple example that will be understandable. If we go in our package name here, you can see for these classes here, we see a Smali file. And specifically what we want to change is the source code of our A class. Because remember, the A class is this one here that hosts our functions with a string equals check. Because a reverse engineer wouldn't actually need to print that secret at all and actually find out what the secret is in order to move on with the app, in order to pass that dialog. An attacker could really just go ahead and change the function's code to always return true. That would just let the user pass for any type of secret that's entered. So let's do that. So I've opened VS Code here, my editor of choice, but feel free to just edit this file with any text editor you prefer. We simply want to take this A file and drag it into VS Code. Actually not like that, but full view. And you can see here, this is not as readable as our Java or Kotlin code, of course. And as I said, you need to learn Smali if you want to do this more often. But you can see we have this function A call here that is relevant. And if we now scroll down a little bit, at the end we can see that a certain value is returned. So this P0. Before that, a new string instance is actually created. Then you can see the init function, or the constructor of the string class, is invoked. And then the equals function is invoked with some kind of object. And in our case, we know that this is the byte array. But what we can now do is we can say all this stuff where we allocate a new string, where we then check for equals, where we move the result to some kind of variable that is then returned. Let's remove that. We don't care about that. We always want to return true, right? So we can just modify this return statement. And the way Booleans work here in Smali code is we just type const/for, and we actually want to store this in the P0 variable. So let's revert this and say we want to return P0, and then above we just inject an instruction with const/for. So we just allocate space for a Boolean, then say P0, that's the variable name, and we say 0x1, so that's the hexadecimal representation of 1. So 1 would mean it's true. So we just create a Boolean variable, we set it to true, and then return that to true Boolean. So now it's not dependent on the string equals check anymore. If we now save the Smali file, then go back to our terminal and use APK tool now again to take these Smali files and all these other files and repackage these modified files into an APK again, and we say APK tool B. And we again refer to, not again refer to the APK, but this time we refer to the folder path. So this one here without .apk, hit enter, then it's building something that says build APK. If we take a look on Finder, going back here once more, actually no, it's inside here in the dist folder. This is now the modified APK after repackaging it with our changes. Well, if we now go to Android Studio and uninstall the previous APK again, like this, uninstall this, take the new one, drag it in here, you will see that we get some kind of error that the install parse failed because there are no certificates, because this APK is not yet signed, and the emulator expects a signed APK. We can quickly do this. That's really nothing I want to go into detail. For that, we just need to make use of two tools. I will paste the command here because it's quite long. So we use this key tool, which is used to actually create a key store. Oops. We want to generate a key. We then create this key store. We call it my key store. We give it an alias, my alias. That becomes relevant later when we want to sign something with this key store. Specify an encryption algorithm, a size for the key and a validity. If we say, let's do it, we need to enter our system password, enter key store password. So the password we want to use for the key store. Let's just use something simple. Okay, that was too simple. Enter that twice. Enter first and last name. All the rest you can really just skip with enter. You just need to specify the name. Hit Y for yes, I want to do this. And now here we have this key store being created. And with this key store, we can now sign our generated APK. So let's actually move this APK out of here. So in our dist folder, we cut this out, go back to our initial folder, and paste this. Okay, it's actually, let's say, keep both and say we rename this one here to repackaged. And now we simply want to take this key store and sign our repackaged APK with it. So we use this jar signer tool for that. Again, specify an algorithm, something for hashing a key store, which is the, not my release key, but I called it my key. So just say my key.key store. And then we refer to the original level 1 or APK with repackaged like this. And also make sure that we refer to my alias, since that's the alias we've set before. If we do this, we need to enter the passphrase for the key store you've set before. Enter that. Unable to open jar file. I don't know, is it actually existing there? Repackaged. Oh, I actually renamed I removed the original one. Let's have this command again, remove original to actually have a real file being resolved. Hit enter, enter the passphrase once more, and now the jar was signed. That's looking good. Let's try to install this again here by opening our Finder, taking the repackaged APK, dragging it on our emulator, and now it was installed. Exciting stuff. Let's open this. Here it is again. We open it. Here's the secret, and we now enter an invalid secret, at least an originally invalid secret. We say verify, and it says it was the correct secret. So all this cryptographic code here with obfuscation and all that stuff, that's worthless if an attacker can just say, okay, you know, this function now returns true in all cases. Because what this shows is you can really inject any type of code at any place in an existing APK. You could just download their website, as I said, where you can just download any APK that is on Google Play. So an attacker could inject malicious code, and an attacker could inject code that maybe logs user credentials to some kind of backend server and then redistribute that app, maybe on another app store, maybe on some kind of website. The possibilities to cause harm with this are really infinite. So I think it becomes clear how important this is really if you have a serious business. If you just develop a 2-screen to-do app or so for a hobby project and you publish this on Google Play, then it's unlikely that someone could cause real harm by reverse engineering that. But if you have a serious business application, you have a user base, you need to protect sensitive data, you need to protect API keys, you need to protect cryptographic keys, then this is something you can't ignore. I always say that security is not important until it becomes important. And when it becomes important, then it's typically too late. So what can we really do against that? And the good news is we can do a lot. What we of course can't prevent is that a reverse engineer might get an instance of our APK. As I said, on Google Play, they could just download it. But what we can really achieve is we can make it so hard for them to actually really find a serious place where to change something in our app, to make it super difficult to really make changes in our reverse engineered code that make sense. And this is also where we come to this video's sponsor, which is GuardSquare. So thanks a lot. I also learned a lot since they taught me a lot how these security tools work. If you don't know GuardSquare, they are pretty much the makers of ProGuard. If you're an Android developer and you build some sort of apps, you will know ProGuard. And they have a tool called DexGuard, which is pretty much ProGuard on steroids. And this tool applies so many measures of security. So what it will do is it will apply encryption, multiple different obfuscation techniques, and runtime checks of your source code. So that it would be impossible to see any plain text API key, any plain text cryptographic key in your code, because that would be encrypted multiple times. And if you would decompile the app, you would only see that encrypted version. Same thing for all other strings. So there would not be an as easy entry point for an attacker like here in main activity, where it says this is the correct secret, when attacker immediately knows where to look for, but such strings wouldn't even appear in the decompiled version because they would be encrypted multiple times. Then in addition to name obfuscation, which R8 applies, that's simply renaming the stuff, you've seen this doesn't do a lot at all in terms of security. In addition to that, DexGuard applies so-called code obfuscation. That's another form of obfuscation, which pretty much changes the structure of your source code to make it way, way harder to understand without changing its behavior. So this works, for example, by obfuscating arithmetic operators. So instead of having a simple A plus B call, they would inject some bit shifting operations, maybe some AND and OR operators, which don't change the end result, but make it super hard to actually understand what kind of arithmetic operation is going on there. But that's still not it. They also apply so-called code virtualization. So it means your final APK actually has an embedded virtual machine which runs its instructions in some kind of custom intermediate language, which also makes it way, way harder for someone to actually understand what's going on. And they also inject certain extra code that is on the one hand able to detect when the signing information changed. So when an attacker has to re-sign the APK like we did it after using APK tool, we can of course use our own key store, but the moment we use our own key store, the signing information has changed. And that is something that an APK that was repackaged with a DexGuard can actually detect. In these cases, there's just code injected that will crash the app. So if an attacker actually re-signs your repackaged APK with their own key store, and they would open it, it would simply crash. The APK, after using DexGuard, would also detect something like if Frida is injected, if someone is listening to certain things on runtime, and would crash the app as a result of that. It can even detect if the device is a rooted device, so has root privileges. It can detect if your app is running on an emulator. And it can even detect if a current debugger is attached, which is also an option to actually get information of a running process. And just to show you how an APK would actually look like after having DexGuard applied and all their security measures, I have this protected APK. If we drag this here in JetX, then, well, we do see the source code here, but let's take a look. We open this package again. And just opening main activity, you can see how much stuff is going on there. If we take a look in here, does not look in any way how the original app looked like. So we would have no idea what's actually going on here. And even if we try to search for something like secret or so, which was definitely contained in the string where it printed that's the correct secret, then you can see that's not contained in this file at all. So there is no real entry point for an attacker at all in order to change something. And if they would change something, even if they would spend all the time in the world to really find out what this code is doing under the hood and change something with this code, as I said, DexGuard detects that there are changes made. And you could of course also look for specific equals checks here in this code to see which equal check might actually be the one that has that checks in the dialog. On the one hand, you will find a ton of equal checks here. So you would need to brute force every single equals check here in the code base, which would be gigantic for a real project. And this is really just a project with an edit text and a button. And even after brute forcing it, you would not be able to find the equals check because class encryption has been applied. The classes with these equal checks have been encrypted. You won't be able to find these like that in the source code anymore. And yes, technically you could still inject certain source code with APK tool as we've seen, but how do you know where to inject that? That's also virtually impossible with code that is secured like this with DexGuard. So if you have a serious app, you have maybe a user base that you need to protect. If you have sensitive information like API keys in your code base, if there is any form of harm someone could make if they had full access to your source code, then please use DexGuard. These guys from GuardSquare really understand so much about mobile application security. For a long while, I also believed that R8 is actually enough to do that until I started reverse engineering myself and playing around with that. You've seen it doesn't do anything. Any somewhat professional reverse engineer will laugh about R8 obfuscation. So if you want to really protect your app, click the link down below. Check out DexGuard, the tool from GuardSquare. It is a paid tool, but as I said, it's so much smarter to actually pay a little bit in advance for a really, really good tool than to have a huge disaster at some point because someone cracked your app, maybe published sensitive data, uses your API key to make requests in your name with your payment method. So think about how big the damage could be if someone would get that information, and that is very, very, very likely way higher than the investment of DexGuard. Thanks so much, GuardSquare, for sponsoring this. It's a great tool. Thanks so much for watching this video. I think it was really interesting to understand this mobile application security a bit more in depth. So let me know down below if you want more videos like these. And other than that, thanks so much for watching. I will see you back in the next video. Have an amazing rest of your week. Bye-bye.